let's go ahead and let's talk about this next thing. Um, uh, this is the O-type blood problem one more time. Here's what the histogram looks like. Looks oh, I'm sorry, I change this to 5 and 0.25. That histogram looks a lot like the dots that are done here. All right. And what do we find? We find that that shape is skew right. What about the center of this distribution? Well, if I look at that number, 23%, and I add another 39%, it seems like once I add these two numbers, I'm over the 50% threshold. I could say that the median of this distribution is 1. But since we have this distribution all set here, why don't we see if we can get Desmos to give us the mean of this distribution? To do that, we assign to a variable, and I'm going to use capital B here and say equals. I'm going to say that this capital letter B is our distribution. Actually, I should be consistent with our things. Let's use capital X. Now, once we declare X to be this distribution, I can ask Desmos things like, hey, using that distribution X, tell me the mean. And it tells me that the mean is 1.25. And that makes sense. It's a skew right distribution. And so we expect that the mean will be further toward the tail than the median. All right. Spread. We could easily calculate the range. The range would be the highest value, 5, minus the lowest value, 0. That's 5. But what about the standard deviation? Maybe we could have Desmos tell us the standard deviation using the command x dot and then standard deviation. Oh, deviation of 1.968 or 0.968. And again, we can get that out of the calculator. All right. Now, note that this 1.25 might be able to be found another way. And that is, it's just generally understood that for a binomial distribution, the expected outcome is the number of trials times the probability. Think of it this way. If I do 100 coin tosses, how many heads do we expect? Well, that's certainly a binomial situation. And we expect 100 times 0.5, we expect 50 heads, 50 successes, n times p, right? And you could see that this 1.25 could have been thought of as 5 trials with a probability of success of 0.25. And that's our 1.25. The standard deviation has this crazy formula, and we might see that indeed the square root of 5 times 0.25 times 0.75 ends up being that number. Okay, please note that these formulas are only for binomial distributions. They don't work for other distributions. Let's see this in action. Mr. Bullard's AP Statistics class did the activity on page 340 of our textbook, where students were asked to determine whether they can taste the difference between bottled water and tap water. There are 21 students in the class. If we assume that the students in the class cannot tell tap water from bottled water, then each one is basically guessing with a 1/3 chance of being correct. Let X be the number of students who correctly identify the cup containing the different type of water. Okay, so X, is this binomial? Well, every trial ends in success or failure. Each trial is independent. That sounds good. Set number of trials. Yep, 21. And probability of success, as it's stated in the problem, is 1/3. So we meet each of the criteria. And I'm just going to give those check marks. But reminding ourselves probability is 1/3 and n is 21. I guess I should say that we do have these being independent And we do think every trial ends in success or failure, so it is binary. What is the standard deviation of X? Well, the mean of X, sometimes also called the expected value of X, is n times P, or 21 times 1/3, which is 7. What about the standard deviation? That would be the square root of n times P times 1 minus P, which is the square root of 21 times 1/3 times 2/3. I think I'm going to have to resort to desmos for that. And so that is SQRT square root 21 times 1/3 times 2/3 and 2.16. 2.16. All right. And what do each of these mean in the context of this problem? Um, over many groups of 21, the average number of successful guesses is 7. And that's our description of the mean. But over many groups of 21, the number of correct guesses differed from the mean by 2.16 guesses on average. There we go. There's our descriptions. Now, let's say they did the experiment. If they were guessing, we'd expect about 7. They got 13. That sounds really far away from 7. So we might think that maybe they can tell the difference between the bottled water and the tap water. But maybe we should also try to tell this tale using probabilities. What's the probability of exactly 13? Now, let's say we'll give them the benefit of the doubt, 13 or more extreme out there. That's all. We'll calculate that probability. So let's go back to here. Maybe I'll just modify this. Let's say X is tw 21 people with a 1/3 chance of guessing correctly. And we would like to know what's the probability of getting 13 or more, which means 13 to 21 of them correct. Ooh, that's a pretty low probability. You can see all those low probabilities being added up. Um, so 0.007, 0.007, which is less than 5%, we might think the students weren't guessing because this outcome is much, much higher than you would expect it if they were guessing, because probability is less than our surprise factor of 0.05. All right. So let's go back to the multiple choice question. Um, so if you were doing again 10 multiple choice questions with a 1/5 probability of success of guessing correctly, um, what do we think about the mean? Well, that mean would be 10 times 1/5, which would be 2. And we interpret that value. We expect two correct answers over many guessing students. And I'll just put in on average. Okay. What about that standard deviation? The square root of 10 times 1/5 times 2/5. Okay, let's calculate that. Um, I might do it two ways. I might put in 10 questions with a 1/5 probability here and see the standard deviation is 1.264. Or I might calculate it by hand. 10 times 1/5, and the probability of getting it wrong is 4/5, and there's that same number. All right. In its interpretation, again, over many guessing students, the number of correct answers differs from the mean. That's our standard definition of a standard deviation by 1.264 guesses. Again, on average. Okay. What's the probability that the number of the correct guesses is more than two standard deviations above the mean? Well, let's see. The mean plus two standard deviations. Well, that's 2 plus 2 times 1.264. Well, let's type that in. 2 plus 2 times 1.264. It's a 4.528. 0.528. So what are we asking? The probability that X is greater than 4.528. Well, see, if we go back up to here, 10, 5, that's right. And I could say I want only the right tail, and I want to be greater than 4.528. And you can see if we can spread that out a little bit. There's our distribution. Doesn't include 4, but includes 5 and more. So that probability is about 3.3%, 0.033, right? And that concludes that problem. Now we get into the part of the lecture that talks about how we might, quote unquote, cheat in statistics. Um, the binomial distribution is based on those assumptions that are in the binomial setting. So one of them is independence. All right. Um, I want you to imagine that we're back in the cereal box problem, and there's 100,000 boxes. Each of them has a card. 20,000 cards of each of the NASCAR drivers, so on and so forth. And so we might say that we'd like to do this problem as binomial, but it's officially not. Because once you open up the first box and you kick a card, and either it's the card that you want, a success, or it's the card that you don't want, it's not a success, whatever happens, you're not going to put the card back into the box and then reopen the box. That box is gone. The probability of success has now changed either for to make it higher probability or lower probability, but they're not independent. These trials are not independent. So the way we should do this calculation is on the first box, we got 80 out of 100,000. The second box, third box, so on and so forth. But let's say, just for the sake of argument, that you forgot about that. Let's say you forgot about the independence condition and you simply calculated the probability of that occurrence. The probability that it was NCR, how many trials? 6 trials each, and I'm looking for and I'm thinking that I won't get any Danica Patrick cards, so 0 successes. And I multiply this by the probability that I would have a success, which is 20,000 over 100,000, which is zero point 0.2 to the power of 0 successes. And I multiply that by zero point 0.8 to the power of 6 failures. So 0.262144. 262.262144. So that's me calculating it wrongly using binomial. Here's me calculated correctly, taking into account the lack of independence. And you see, the only difference between these two numbers is like the 6th digit. And let's face it, at the 6th digit, do we really even care? And the answer is no, we don't. Here's what we're going to say. Sometimes when we are doing these problems, especially when we are sampling without replacement, that means we're not putting something back in before we pull it back out, that we think that as long as the population, or as long as the sample size is really, really small compared to the population, we're independent enough that we're good enough to say we're close enough to use the binomial tool, and it's not going to matter in any material way. So if we're sampling without replacement, we can still use the binomial distribution as long as the sample size is much smaller than the population size. How much smaller? No more than 10% of the population. And certainly 6 is much less than 10% of the population to 100,000, right? Now, be careful. We really do need to meet this criteria, because if we ignore this criteria and we just go ahead, we might end up with this situation. Hey, there's 8 batteries in a drawer. We know that 6 of them are good, and we choose 4, and we hope our calculator works when we put those 4 batteries in. What's the probability that we get 4 successes out of those 4 trials? And we calculate this probability. But the actual probability, if we did take into account the lack of independence, is much, much smaller. Why? Because we didn't meet that 10% condition. We chose we chose 4 out of 8. We chose sampling 4 out of the distribution, 4 out of 8. That's 50% of the population, 50%, not less than 10%. So you can see that if we ignore that situation, we indeed get bogus numbers. All right, last bit. Another way to quote unquote cheat. It just so happens that binomial distributions can be approximated by using a normal distribution. That sometimes the distribution looks skewed, and that's not normal. But As the sample sizes get bigger, the binomial distribution looks more and more normal. So it comes down to this question, how big does the sample size have to be in order for the binomial distribution to be approximately normal? And that answer is as long as we get n times p greater than 10. Well, n times p is the expected number of successes. So as long as we expect at least 10 successes, if n times p is greater than 10, or, sorry, and n times 1 minus p and n times 1 minus p is really the expected number of failures. So as long as we expect 10 successes and 10 failures, then we say it is okay to think that the normal distribution is a reasonable estimate. Um, the binomial distribution could be reasonably estimated by using the normal distribution, right? Again, two criteria. So we had the 10% criteria, which says we can think of it as being independent enough. And the second criteria, if we expect at least 10 failures and 10 successes, we can we can um, say that the binomial distribution can be approximated with a normal distribution. All right. Sample survey shows that fewer people enjoy shopping than in the past. A survey asks a nationwide random sample of 2,500 adults if they agree or disagree to the statement, I like buying new clothes, but shopping is often frustrating and time consuming. Population that the poll wants to draw conclusions about is residents 18 and over. Suppose that exactly 60% would agree to that statement. Let's see about uh, using uh, our newfound skills. Is X approximately binomial just variable? Well, let's see. Binary, yeah, I think success is agreeing. And either someone agrees or they don't agree. So we meet that criteria. Independent, well, I think we're independent enough because we're going to sample but without replacement. So we'll have to say is 2,500 less than 1/10 n, where n is the number of people 18 or over. Well, I think certainly the number of people 18 and over is much bigger, 1/10 of it is much bigger than 2,500. So we're going to say we meet that criteria. Is there a set number of trials? Yep, the number of trials is 2,500. And is there the same probability for each trial? And that is indeed probability of success is 0.6. Now, again, we use this condition to check to see if we're independent enough. Now, do you think we might use the normal approximation? Well, let's find out. What is n times p? Well, n times p is 2,500 times 0.6, which ends up being 1,500. And 1,500 is definitely greater than or equal to 10. So we give ourselves a check mark on that. What about n times 1 minus p, or 2,500 times 0.4? Well, that ends up being 1,000. 1,000 is greater than 10. And so, yes, indeed, binomial 2,500 comma 0.6 can be approximated by using the normal distribution with 1,500 being the mean, because that's the expected number. And what is the standard deviation of this? Square root of 2,500 times 0.6 times 0.4. One more time for desmos, the square root of 2500 times 0.6 times 0.4, 24.49. 24.49. Okay, so we think that this is a good representation. So let's do the normal distribution calculation. Let's draw that normal distribution. Let's center it at 1500. Let's recognize that the standard deviation is about 25. So we're about 1525, 1550, 1475, 1450 in our distribution. And we're trying to find the probability of 7 or 1520 or more. So the probability that X is greater than or equal to 1520 is going to be a normal distribution problem. The normal distribution with 1500, comma, I don't feel like typing this in again, so I'm going to copy it and paste it. And we want the right tail, and we want to be 1520 or greater. So about 20.7%. 20.7%. And there we go. There's using it. Now, you're like, we could have used binomial, and we would have gotten a similar answer. All right. And that concludes this this lecture, 6.3.1.